understand when we first learned derivatives, you understood what a derivative is. Essentially, what's a derivative in like the simplest possible way? That was awesome. The slope of a tangent line. That was perfect, right? That's what a derivative is. We learned that. And we actually learned this kind of formula initially where we use slope formula and a whole bunch of secant lines and got them closer and closer and closer using limit, right? And then we found, yeah, that was great, but we got this shortcut to do it, correct? All right, same idea today. But to do that, we first have to understand, we've already started doing the antiderivative, right? So you get this idea that we go backwards. What does that backward represent, though? Again, we know what a derivative gives us. So the question today is, what really does an integral give us? If a derivative is a slope, and some of you may already know this, in relation to a curve, what does an integral give us? And don't say the original function. That's not what I'm looking for. So that's what we're going to focus on today. We're going to focus on area under a curve. This, for those of you going on to Calc 2, is huge. It'll follow you through. Those of you going on to physics, lots of applications with both derivatives, meaning slopes, and with integrals, areas under a curve. Parts of it is. I'll tell you what parts, don't worry. I'm very good at saying you will need to do one of these on the exam. And then you won't have to do this, but I just want you to follow me for a minute, kind of thing. Damien. The antiderivative gives you a family of functions, right? Not the specific. It'll give you a family of functions. But an antiderivative between 2 points, which you're going to find out today, will give you an area between a curve and an x-axis. We're going to see where that comes from, okay? So, but we're not going to start with integrals. We're going to get there, the very end, and you're going to be happy when we get there. We're going to start with an understanding of how can we calculate an area under a curve. And we're going to do it a bit rudimentary at first, okay? So, 5.1, and I will do my best to type slow, so it's me, is basically approximating areas under a curve. What did he say? Okay. Remember, we are recording. Not that I don't think we can hear you guys, but we are recording. I don't know, did anybody watch the other video? No, you only needed it if you needed. If you had the notes, you probably didn't need to see the video. So I don't. Usually, when I watch other professors who do this, you don't hear the teachers. You don't hear the students. Sorry, you don't hear the students. So we're going to start with a nice simple function to get the idea, and we're going to start with the function y equals x squared. And I just want to have my book open to make sure it's correct terminology and fun stuff like that. So we're going to start with just, yeah, I like that. Y equals x squared, because that's a function you all know how to sketch. And we're going to look at y equals x squared from, say, 1 to 8. So if I were to draw it, right, you all know what y equals x squared is, right? Come on. What's the graph of y equals x squared? You can have the little finger. Air draw. It's quadratic, right at 0. It's the most basic quadratic, right? So I only want to look at it from 0, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to exaggerate it and kind of fatten it a little, or I'm not going to have room on my paper. All right. So clearly it's not drawn to a perfect square, but if this, you know, is a really wide quadratic. So in other words, my y-axis is shrunk, right? Because if this is an 8, everybody, what's up here? 60? 64, thank you. All right, so my y-axis is obviously shrunk. So how do we get this area under a curve? Well, if we had a perfectly straight line between 1 and 8, it would be easy to get an area under a curve because that's a right triangle, correct? And you all know, oh, the area of a triangle is half the area of a rectangle. So whatever this is, that is, I can calculate it quite easily. Any geometric figure that you know of, circles even, you can calculate the area because you have formulas for them. We don't have a formula for this particular type of curve. So what we do is we partition it, and think about it, partitioning it into rectangles because we're approximating, right? So let's suppose I want to keep it simple and I want to use 4 rectangles. So the number of rectangles you use is referred to as your n value. So I'm going to use 4 rectangles, and I'll start at 8. Okay, well, let's think about this for a minute. It is a curve. It just came out a little straight. Do you want me to fix it? I'll try to get it curvier. That really didn't work. It's a curve. It's a curve. All right, it's y equals x squared, so it's a curve. Now, all right, let's think about this for a minute. I'm going from 0 to 8. I want 4 rectangles. How wide are each of those rectangles? 2. Everyone agree? 2? Okay. So that actually has a value as well. We're going to call that, for now, we're going to call it delta x. Delta x is going to represent the width of each rectangle. And delta x is pretty easy to calculate. So I'm giving you little pieces of formula along the way, all right? So we're going to call this A. And we're going to go from A to B. That's our interval. And we always label intervals like A to B. So that's pretty easy. So that means delta x is, we can come up with a formula for delta x, right? Start with, how did you come up with that? Well, you took 8 minus 0 divided by n, right? So wouldn't the formula for delta x look something like, take your n value over n, which in this case is 8 minus 0 over 4, 2. All right? That's our width of every rectangle. So let's draw those rectangles. Think about how they can be drawn, though. So I'm going to start with 8. So that means, sorry, the paper's gone. I'm going to need information at 6, 4, and 2, right? That makes sense? So yes, Lucy. Well, we're doing that right now. So we can draw the rectangles. Katie. Because I want 4 rectangles between 0 and 8. Right? So yeah, they're going to be two with each. Okay? And we can change that. Kaya. Huh? Oh, you're going to see that. Hold off on that. All right? Because again, we're approximating. We're going to use something we know how to find the area of to approximate something we don't have a formula to find the area of. Yeah, so let's take a look at what happens. So if there's my rectangle between 6 and 8, there's my rectangle between 4 and 6. There's my rectangle between, right? And there's my rectangle. And what I really only want is this. Clearly doing it this way is going to cause our approximation to be what? Larger than our actual area, correct? This is actually called a left-hand area, or right-hand, sorry. Now, why is that? Look at each rectangle, okay? Check out each rectangle. Which side of the rectangle is actually touching the curve? The right-hand side. Do you see that? Every rectangle, do you see how it's the right-hand side touching the curve? That's called a right-hand side area in this case. So we're going to still calculate. We're going to calculate this really quickly. How are we going to calculate this really quickly? Well, there's rectangle 1, rectangle 2, rectangle 3, and rectangle 4. Let's start with the first rectangle, everybody. The width is the same for every rectangle, right? What's the width? So my first rectangle, now we've got to figure out the length of that rectangle. Again, we're using right-hand side. So the length of the rectangle is plugging in 2 into x squared. So what's the length of that rectangle? I know it doesn't look very good. 4. Does everyone agree? Because it's x squared. It's at the point on the curve of x squared, right? So right here is 4. So this first rectangle's 2 by 4. Let's go to the second rectangle. The width stays the same, right? What is my length of that rectangle? I got to do 4 squared. That's 16. Third rectangle. Fourth rectangle. Fourth rectangle. Okay, this is where I said, no. So let's think about what we just did also. I took each delta x, right? Do you see that? For each rectangle, for rectangle 1, and I multiplied it. So now I'm going to call these x's. I'm going to call this 0 value x sub 0 because it's the initial x I'm starting with. That's what x sub 0 means, by the way. Then I'm going to call that x sub 1. So these rectangles are delta x times f of x sub 0. Right? Isn't that what we just did? Because again, we're building to a formula here. So you're going to bear with me for a second. And then times, oh, that was x sub 1 times, oh, sorry, f of x sub 1, f of x sub 2, and then delta x. I got to move over a little. Oh, wait. Stop myself. I get so excited. It's not x sub 0. So to understand this formula, go back to the first triangle. We didn't use x sub 0 because we said it was a right-hand area. What did we use? X sub 1. So let me just change the subscripts. It's 1, 2, 3, 4. All right, that's what we did. Oh, and while he's asking, could you all just calculate that for me real quick? We're not using it because it's the y-intercept. We just picked it. We could go from 2 to 8. We can go from 4 to 8. We can go from anything. I just picked that. Yeah, that's fine. That's fine. What do you mean 2? Why y-intercept? I guess I'm wondering. You can, yeah, ask. Mm-hmm. Yeah, we're going to talk about it. Yeah, no. Yeah, that's fine. We would use whatever. It would be x squared plus 1. We'd be plugging our number into. Plus 1. Yeah. You can erase that. You can only erase what's underneath. Yeah. That's good. All right, what do we get for our area, everybody? Awesome. That's a left-hand, right-hand approximation. Sorry, I keep wanting to call that left. All right, now we're going to do the same thing, but this time we're going to switch it to the left. Okay? So you're going to ask me, what am I going to have to do on the test? See what I just did without all the delta, just the calculation? You will have to do that on the test. Okay.
So, sorry, I need to go back a little bit.
Mm-hmm.
For whether it's AR equals to, why are you responding to 2 times and side?
Oh, because
That's, 200.
this first rectangle, right? This is delta x. That's 2. 0 to 2 is 2. An area of a rectangle is length times width. So now I need, how tall is the rectangle? Well, that's this point. I got to plug 2 into y equals x squared. That's why it's f of x1 over here. Now, this is good. If you understand it all now, it'll make it much easier as we go through. Delta x is always going to be the same width for every rectangle we're approximating, so it's just delta x. Okay, it's how you calculate it using this formula. It's just going to be delta x.
Just so I can label it properly, this is right hand.
This is a right hand.
What's the next part?
So these are called, and I wasn't going to get to that yet, but we can call them this. These are actually called, they're sums, right? We're summing rectangles. These are called Riemann sums. All right? So this is using what we call a Riemann sum. It's R-E-I-M-A-N-N. So it's actually using an area, using a right-hand Riemann sum. Okay? We get 240. So now I want you to figure out what would this look like if we did a left-hand sum. So I'm going to redraw the graph. Okay? So let's do a left-hand Riemann sum. Well, for that, let's think about it. I still have the same graph. I'm still going to 8. Now we know for sure I only need to put what? 4, 6, 2. Notice my delta x does not change. If I'm still doing n equals 4, which you will be given, delta x doesn't change, right? That's still 2. The look of our triangles changes, though. In fact, I don't know why I put, let's get rid of that line. Because now the triangle is going to have the left-hand side touching. So at any given value, I'm just going to use 6 for a second. When I go and draw my rectangle between 6 and 8, we know there's a rectangle between 6 and 8. I want the left side to touch. Do you see that? I want the left side to touch. I want the left side to touch. And you're right, what happens when the left side touches here? It's 0, which is fine. Now, this area is going to be where? If the other one is going to be an over approximation of the area, this one's clearly going to be an under approximation. But let's calculate it just real quick. We're just going to do the calculation. I'm not going to do all the other stuff. So remember, it's delta x. But in this time, here's the difference, though. It's not, it's now delta x. Instead of starting at f of x sub 1, because we're using the left, we're actually starting at x sub 0. We're starting at the first value. Do you see that? That's a big difference. I just said to do it. All right, look at this rectangle. Right? Right there. Isn't this the left side of the rectangle? The left side is touching the curve, not the right side. In the other one, the right side was touching the curve, not the left side. All right, so that's the idea. So it does change a little bit. Sorry, I keep going back and forth. In that we have x sub 1, delta x, and we're only going to go up to So let's look at the calculation. The calculation part, I think, is pretty easy. So what changes? So area from the left, my delta x is still 2. But when I plug in, I got to use 0 first now because that's the left-hand side. What happens when you plug in 0? What do you get?
0.
So it's actually 2 times 0. Remember, we said this is going to be an underestimate. Then, now I use 2, right? What's 2 squared, everybody? Now I use the 4. What's 4 squared? And I use the 6. Notice I don't go to the 8 on this one, right? I use the 6, which is 36. Give me that calculation. Clearly, it's going to be an underestimate. What is it? 112? We good? So what do we know right now? Our area is somewhere between, actually we don't need the equal to sign because there's no way it's equal to that. Wrong direction. 112 and 240. Well, that's not a very good approximation. Now, is it? So here's the next step. We're going to stick with our 4. So far, yes, you are going to be asked on the test. On the lab, just so you know, I'm going to give you 1, and you're going to do a left, a right, and a third one that we're going to go with in a second. On the test, I'm just going to ask for 1. It's going to be one of the 3. You'll see the third in a second. All right, and I'm going to give you the end. So that's all you're really doing. That's it. The rest of what we're going to do today is conceptual for me to show you why this becomes an integral. Now, we did the left, we did the right. Where do you think it might be better to hit the curve? In the middle. In other words, we could do what we call a midpoint area. So let's draw the graph again and see what we mean by that. Okay, I still need to go, I'm just going to do 2, 4, 6, 8. So the best thing to do is kind of just pick one triangle to start with. I'm going to start with the last triangle because there's more room to see it. Does that make sense? And to do that, oh, well, what's directly between? I'm going to go right to the middle. And that is what's going to hit the curve. When we call it a middle, that means that's the height of your rectangle. It's going to be right there smack in the middle. Then you're going to draw it in both directions. Why is that a better approximation? It's going to give some under and some over. So between 4 and 6, draw a dotted line up to the curve and then draw your rectangle. All right, dotted line up to the curve, draw your rectangle. This one gets really tiny. Draw your rectangle. Why is this a better approximation? You got some over that will hopefully balance out those that are under. Does that make sense? Okay, so to do this midpoint, now it's a little bit different because I need to do, all right, my area now for the midpoint. What didn't change though? Yeah, you still have n equal 4, which means delta x is still 2. All right, so for that first rectangle, we're using 2, but now I've got to go, what's directly between 0 and 2? I give it to you in the beginning. You'll be given. How many rectangles? We could have done 8, but that would have been twice as much work for us. We could have done 16. I just picked 4 because it was short. On the test, I'm not. I think the lab you do 8, but on the test I only give you like a small amount. All right, so let's do that first rectangle, everybody. It's 1. Remember, we're still at y equals x squared. So 1 squared is. Second one, this is now using 3. So what's 3 squared? The fourth one uses 5. And then we're going to end with the... Go ahead and give me that answer. 168? 148. 48, 68. Do I have a third person? 168. 168. Sorry, Andrew. 168 wins. This is math by majority. 168 wins. What? Democracy math.
Finally, a method we all agree on.
So no matter what party you are, you all agree with democracy math. All right. So, yeah, 168 is a better approximation. But guess what? So, but we're not going to get there. We're going to get there in a second. What I want you to do, and this is going to require a bit of math, arithmetic. All right? This one's going to require just a little bit of arithmetic. Yes? I totally get you. There may be reasons why you only have certain lengths in real life where you can't get to a middle length of something. I knew that was going to come up. And every semester I teach a course, I'm going to come up with an example why you have to use a right hand or a left hand. I haven't done it yet. But you reminded me to do it for next semester's class.
We'll see you next semester.
Also, no. Well, unless you want to take me yet again, Brian. You take I'm taking stat 2. Take stat 2. So what I want to do first before we get into this is I want to have you do one. Clearly, we realize the middle's the best, right? So I'm going to have you do a little bit harder of a function. Just do n equals 4. And I'm going to give you the range, and I want you to try to do a middle. We're going to call it a Riemann sum, a midpoint Riemann sum. So here is because we're going to use this function a couple times today. So I want you to take the function. This is going to take a couple minutes. It's going to be a little bit of calculation. We can set it up together, and then I'll have you do the calculations. So there's my function. You don't like that function? I'm going to change the interval to 1, 4. And I'm going to make it easy for you with the Riemann sums and only have you, what would be a nice easy number for me to give if you think about what delta x could be? What would be a nice easy n for me to give you? That would be a lot. 1? No. Think about how you calculate delta x. What would be a nice easy n? Somebody said it. 3.
Because 1 minus 4 is 3.
Yeah, there's nice 3 rectangles you can put between 1 and 4. So I'm going to have you do n equals 3. And what I want you to do is calculate the midpoint, because we did agree that is definitely a better approximation. Riemann sum. So what does this look like? Yeah. Yeah. Just to give you an idea, this is again a parabola. It's very much similar shaped. It looks more like that. Okay. So I don't know. One is somewhere over here. I'll draw the pictures with you, but I want you to do the calculation. So, clearly delta x is what? How did I tell you calculate delta x? You do what? B minus A. So this is A, That's B. So delta X is 4 minus 1 divided by 3. It's just 1. So I made this nice and easy for you. All right. Now remember, you're going in between, so it looks like the best way to draw it is just to pick a rectangle, go in between the two numbers, and hit dotted lines up to the curve. So in other words, between 2 and 3, see how I'm doing dotted lines up to the curve, and then go off in either direction. All right. So go ahead and calculate for me. This is a little harder though, because when you go to calculate it, what kind of numbers? This is why I said get your calculators out today. Because what are we plugging in? 1.5, 2.5, and 3.5. So to calculate your area, it's actually going to be delta X times f of 1.5 plus delta X times f of 2.5, because that's our lengths of our rectangles. Yep. And don't forget, this was your function. So do the calculations for me. That you can do it. And then I'm going to take you on a crazy algebraic journey. That I will tell you, it won't be on the test. It's more conceptual. But do this first. So yeah, delta X is 1. You got to plug each of those in, and then you got to add everything up. We want a majority to come up with the correct answer before we can accept it. Nah. We could do, what do you need? Usually they like 60% for something to, Katie.
So for the first problem, we didn't have an interval. Did you just give us it? Will we always have an interval?
I gave you the interval. I gave you 0 to 4. Yeah. When you're doing this calculation with a finite number of rectangles, you will be given the interval. You will be given the end value. Absolutely. So it'll look just like this problem. So this problem I can give you on the test. I will tell you either midpoint left or right. I will give you the function. I will give you the interval. I will give you the end. It's actually not a hard problem, right? It's kind of an easy. So yes, this first problem on this last test is this. Okay. I'm here at 81 point. Oh, yay! Now, it's an approximation. We agree it's still an approximation, right? What is it? 81. That's awesome. So here's my big question to you all. How can we get a better approximation? More rectangles. Is it 5? Is it 6? Yes! If we could do infinitely many rectangles, couldn't we get an accurate area under that curve? How do we do infinite of anything? Yes. Guys, good. So now, let's have a little fun.
Wait, now I got another question. What's the point of learning all 3 of these if we could just take 11 and get a better answer?
Oh, you're going to see in a second. You are going to see in a second. All right. So to do that, it is going to be easier to work it through with a problem rather than do it with just a bunch of variables. But here's the idea. Do we agree that whatever so far to find each individual rectangle, correct? Didn't we take, oh, I don't know, we took our f of x, whatever it was. I'm going to call it I. All right? We need a subscript. The subscript has to start somewhere and go up. Here's what's nice when you go to infinity. Doesn't matter if it's a left or a right or a mid. Because you're going to infinity and these are getting smaller and smaller, do you think it really matters where you took it from? Not at all. You don't have to worry about that. Okay? Where it's actually because they're essentially becoming a line. You're still going to give an interval. You're still going to be given an interval. It's just how many lines are between that interval. So let me do this. I think I have a nice picture of the infinite. So it's our x value times delta x, right? Wasn't that one individual So pay attention. Okay, you're all going to listen to this first, and then we'll come back. All right. Do we agree this is one rectangle? Whatever xi was, that's your length of your rectangle. That's your width of your rectangle, correct? Now, we're taking n number of rectangles, correct? So we're going to go, does everybody know this symbol? Okay, this is called a summation. If you have never worked with it, it goes like this. So it's a little side thing. And this is important because half of you are going on to Calc 2, and you will do 2 full chapters on summations. But many of you, you see summation often like in middle school. So you probably saw it when you were younger, and then it's forgotten about in math. Here's how summation works. So here's just a quick recap of what a summation is. If I wanted the summation of 1 to 5 of x squared, those of you who took statistics have worked with summations in probability and in different things in stats. You've worked with summations. Yep. So you start with 1, so it becomes 1 squared plus 2 squared plus 3 squared plus 4 squared, and you stop at 5. Should I do the 5th? Squared. That's all a summation is. It's a notation. So does that notation make sense for what we're doing here? Aren't we summing rectangles? And we're summing them from the little I is going to go, we're just going to go from 1 to whatever n is. Wait a minute. Can't just do infinity. I'll show you why in a second. Yes? So the red line is 1 rectangle. So if that's 1 rectangle, what's all of this, everybody? How many rectangles? We're not at infinite. N. This is n rectangles. All right, everyone agree? Now, we want to take n to where? Infinity. To take n to infinity, you need somebody said it, limit. You need a limit. So now we add the limit as n goes to infinity. And now this becomes how many rectangles? That's the formula we're going to use. We're going to do that. All right. I'm going to skip some of the algebra in it, but we're going to do it. Okay? We're going to go to infinity with our rectangles. Visually, it kind of looks crazy because think about it. If this is your function, right? It's like, and here's 1, and there's 4. Right? It's like I can't draw them, right? It's a million. It's more than a million. They get closer and closer together. Which is kind of why I said it doesn't matter if you're taking that rectangle from the left side or the right side, because they essentially, they're going to infinity, so they're becoming almost a straight line up and down. Well, yeah, that's why it's x. The x values are going to be different. So now, there are ways to do this, and it gets a little tricky. Yeah. Yeah, but I'm not making you do this on the test. I just want to show you where it comes from. We're just going to go through one problem together. That's it. I just want to use this one time. It's not like, you'll see in a minute, it's way harder and longer than the limit definition for the derivative, which I did make you do on the test. Yeah, this is a bit more complicated. Yes? No, because you want the number of rectangles to go to infinity. We want the number of rectangles, because we said, if you have 4, you get one number. If you had 20, you get a better approximation. 30, 100. You want the number of rectangles to go. But we want the number of rectangles. All right, so we're going to go back to that problem we did. And again, this is one of those things I just want you to watch. You're not going to have to do it on the test. I'm not going to explain it to you again. I just want to show you it works, because you are now in calculus and you're in a higher level math. You've got to see these things work, right? And how they work algebraically. And there's some cool algebraic stuff that goes on in it to get it there. So so we all agree that's the formula. All right, I'm going to put it off to the side. This is essentially the formula. All right, so I'm going to go back to that problem I gave you, which you already got an approximation of 81.75. We're going to get a better approximation. So here was the formula. The function. Notice I no longer gave you an n because we're taking n to infinity. That's the only difference. We still can get a delta x, though. Well, we can sort of get a delta x. We know delta x is b minus a over n. So what part do we know? We know it's... No, we're just going to use n, 3 over n. 3 over n. That's what our delta x is. Okay? We don't know the width. The width of each triangle is going to get smaller and smaller as you go on. Our initial x value. Oh, well, the initial x value is simply a, which in this case is 1, right? But let's use a for a minute. Everyone agree the initial x value is a. Then x1 is simply going to be that value plus a delta x. Do you agree with that? You get to the next x value by adding the change in x. So then, how would you get to the next x value? You add 2 times changes in x. That agree? How do you get to the third x value? You start at the initial value and add 3 changes in x. All right, so I can go down and say, hey, how do I get to the ith value? your x sub 0 plus I delta x. Well, we have some of this information. We actually have some of it. So x sub I, oh, I know x sub 0. What's x sub 0 in my problem? What's my initial interval value I'm starting with? We decided x sub 0 is a. What's a? All right, so x sub I is 1 plus I. Oh, don't I know delta x? I know something of it. What do I know? All right, so far, all I'm asking you to do is just kind of follow the thought process today. That's it. Right now, just follow. Why do I need that? Well, for this formula we have here, don't I have to calculate f of x sub I? So if f of x is 3x squared minus x plus 9, what's f x sub I equal to? Yes! I said it's a lot of algebra, but don't worry, we'll skip some of the algebra and I'll just give you what it comes out to. I've got to take this x sub I and plug it in for x. So that becomes 1 plus, can I change this to 3I over n? Are we good with that? Yeah, because I times 3 over n is 3I over n squared minus all right, you want to simplify that? Do you want to simplify or you want me to just give it to you simplified?
Just give it to us.
You all understand, though, as a calculus student, you are all capable of simplifying that, correct? Can you all disagree with me so I feel good?
Yes.
You're squaring a binomial. It just happens to have fractions in it.
It's scary.
Yeah. So is everyone okay with, I'm not going to make you do this. Everyone gets, this can be simplified. You have to square it. You got to distribute your negative, combine all your like terms, right? Lucy. Say that again. I couldn't. How do I get what? Oh, x sub 0 is our initial value on our interval, which is our a, right? What is a in this particular problem? 1. So if x sub 0 is a and a is 1, that's how I replaced it. All right, you want me to just give it to you? Come on, don't you want to like do a little no? So after a lot of algebra magic, which you can try on your own if you want to, so there, write in your notes, after all the algebra magic, my f of x sub I becomes that function. Okay? After all the algebra magic. Now I can go, and I'm going to plug everything into my limit formula. So you have to just trust me on the algebra magic. It's, again, it is something you are capable of doing. All right, so let's plug it into our formula. So the formula says, well, my actual area, right, because that's what I'm looking for, is equal to the limit as n goes to infinity Yeah, but if you take notes, you remember it. Ding. So I'm going to replace my function with 27i squared over n squared plus 15i over n plus 11. And what am I multiplying that by? Oh, so what's the first thing I'm going to do? I'm going to distribute that through, correct? Well, doesn't that make sense? So I'm going to go ahead and distribute. I get 81, right? Some of this math you can help me with. 81 I squared over n squared, check me, over 45 I over n. Oh, this one's cubed. You weren't checking me, right? Is that cubed or is that squared? That was cubed. Because it's, look, it's n times n squared is n cubed. So I said you got to watch me. And then that one's squared. And then the last one is just 33 over n. Okay. So this is where summations come into play. All right? And I got to give you a little brief statement about summations off to the side here. Okay? So summations work very much like everything else you've learned this year. Limits, derivatives. In that, if you have the summation, and doesn't matter what it's going to, by the way, of c to the n, where c is a constant, right? You can pull the constant out front. If the only thing that needs to be with the summation is what's being summed, the n. Okay, does that make sense? All right. Also, if you have the summation, guess what you can do? Instead of doing the summation of all of them as a whole, what could you do? You could take the summation of each individually. So these are just properties of summations. But they shouldn't be new to you because limits work the same way. Derivatives work the same way. They apply the same properties. Now, that being said, let's talk about this one for a minute. Let's talk about the summation of 1. Because, like, well, what's the summation of 1? And let's do the summation of 1 if I equals 1 to 5. What do you think the summation of 1 is? I know there's no I in the problem, and that doesn't matter. It's actually, you're summing 1 how many times? Let me say that again. You're summing the number 1 how many times? 5 times. What do you think it equals? Yeah. So the first rule is the summation of anything from 1 to n of 1 is just n. All right? That's one of the first basic rules of summation. The next one is if you are summing an I. Constant. It's a constant you can pull out. That's all that tells you. It's constants you can pull out. So let's talk about the difference between these two. This one is 1 plus 1 plus 1 plus 1 plus 1 plus 1. Okay? This one, because I put an I there, is 1 plus 0, 2, then plus 3, then plus 4, then plus 5. You see the difference between those two? If you're summing 1, you're just summing the number 1 5 times. But if you're summing I, that I changes for each iteration. So it becomes 1 plus 2 plus 3 plus 4 plus 5. You see the difference? So if it's 100, you're summing the first 100 values. Okay? There's actually a formula for that. You might have remembered that. Lucy? N. If n goes to 100, You're summing 1 plus 2 plus 3 plus 4 plus 5. There was a quick way of doing that. You may have done it at some point. Factorial goes the other way. 100 factorial is 100 times 99 times 98. Okay? Now, the summation is actually, it works really well, and it's simply whatever that last number is. So say it was 100. You can add up the first 100 numbers real quick. You take that, you multiply it by one more than that, and you divide by 2. If you don't believe me, try it with like 5. It works. In other words, what's the sum of the first 5 numbers? We can do this in our head. 1 plus 2 plus 3 plus 4 plus 5. All right, everyone agrees. Sum of the first 5 numbers is 15, right?
Sorry.
Everyone agrees. 1 plus 2 plus 3 plus 4 plus 5 is 15. Okay. So 5 times 6 divided by 2 is what, everybody? 15. Works. That's how you quickly sum a set of numbers. Now, there's also a cool formula for I squared, and we're going to need these into our formula in a minute. I squared, and those of you going on to Calc 2, which I know it's a good amount of you, you're going to see these a lot. And some of you are going, yep, that's why I'm dazed right now, because I'm not doing that. It's all good. We got to, you know, work with it. All right, this one's a little more complicated, but it works. It's n times n plus 1. This one I always got to look up because I always forget. It's n times n plus 1 times 2n plus 1 over 6, I believe, yeah. Yeah, going to Calc 2, you couldn't know these. Oh, there's cool proofs for that, but we don't have time to do that. When I went to college, all we did was proofs. I is how many times you're going to do it, right? Well, so in this one, yes, I is your variable. I is your variable that's changing, right? So this actually becomes 1 squared plus 2 squared plus 3 squared. So yeah, it's kind of like a variable. You could have x. You could have the summation of x equaling 1 to n of x squared. Same thing. Yeah. Oh, that's the whole definition of summation. That's just the whole, how you define a summation, is putting the next value in. Yeah. After you get past Calc 1, you'll do more proofs, even here. Yeah. Yeah, no, it's more of a change in time. 30, 40, 10 years ago when I was in college, we did a lot of proofs all the time in the 80s. And then as education progressed and technology became a lot more, proofs started to go away. That's all. Kyle. Yeah, this is just, we have to use these because as you can tell, I have an I squared and I have an I. So we have to know those. So I'm just giving them to you. Yeah, we're going to come back to this problem now, and we're going to plug that in to get an answer. Because we got to solve it. We're going to solve that. But this was a little side thing, preview. It'll be taught. It'll be taught in Calc 2, but it's going to be really helpful if you see them. Because then you're not the student in the class and says, my professor never showed me that. Oh no, a lot of us do this. Not everybody, a lot of us do. So, all right, we're going to work a lot of magic here, but let's take a look at it. So where are we at now? I'm going to apply some of these rules. And then I'm going to get to something that you can easily calculate. And I'm going to show you the shortcut way, which you're going to love. Okay? So when I go ahead and do this, well, a couple things I can do here. I can, let me get rid of this for a second. I'm going to break each of these up into 3 summations, first of all. Does everybody see that? And as I break them up into 3 separate summations, anything that's a constant, I'm going to pull outside of the summation. So watch. The first one, what's a constant? Well, 81 and also the end. The end's a constant. It doesn't change within our summation. Remember, the summation is only changing the I values, not the n. We don't have anything for n yet. We'll deal with that in a minute with the limit. So right now, I can say, okay, this is the limit of, let's do 81 over n cubed summation of xi squared. Plus, what gets pulled out of the next one? Summation of I plus, do you see everything gets pulled out, but I still got to put a summation there. So what do you think is left? A 1. Yeah, summation 1 is basically what ends up being left. Now, as you can see, what we would end up doing is actually plugging in and this is where you're going to be like, oh my God, that's an infinity sign. So what does this end up being? It ends up being the limit of 81 over n cubed times, what's I squared? Plus 45 over n squared times 6. So there's a 6 there, right? Yeah, I need a 6 in the denominator. Sorry, I forgot my 6. The next one is times n plus 1 over 2 plus 33 over n times n. So this is where you have to stop and think for a minute. Because as you can imagine, we can do this. We would have to distribute everything out, correct? Distribute everything out. But I want to ask you a question because you have worked with limits. When we work with limits like this, what is the only pieces we actually cared about? The highest exponents. The ones out front. The only thing we actually cared about was this piece and this piece because everything else, when you divided, went to where? 0. So how does that help us right now? I don't need to multiply everything out. All I need are what's going to be my highest exponents. And that's it. So, this, using the idea of a limit, or because I'm taking a limit, I only care about the first exponent on each. So when I look at that first one, isn't it 81 times 2, which is 162n cubed? Do you agree? Do you see what I did there? And the reason I got rid of everything is because when I take the limit, that all goes to 0 anyway. So I'm doing a shortcut. You can work it out. You'll get the same answer. It'll take you a lot longer. Now, the next piece, all I want is 45n squared, right? Over 2n squared. You agree? The last piece is, well, it's just 30. Yeah. But we'll do it 33n over n, whatever. Because I only care about those, all I care about are those coefficients, right? When I take the limit, don't I just get calculate it. I told you this was a lot longer than that. 82.5? 82.5? That's not an approximation. That is actually the area. What was our best approximation? 81.75. What did we get? 82.5. I substituted the I squared with that formula that I gave you. That would take a long time. That's a proof, and we can do it, but it will take. We're not doing it. Okay. Yeah. If you want to see, it's theorem 5.1 gives them to you. You would have to just Google proof of the summation of x squared. You'll get it. Go on. Yeah. So we decided that we only needed those first terms. We didn't care about the rest because the idea is if you're going to infinity, you're dividing by that highest exponent. They always went to 0 anyway, so we can get rid of them. We'd only cared about what coefficients we end up here. Because that when you take a limit to infinity and they're the same, that's all that matters. So what we did is enough work to say, okay, it's going to be an 81 times a 2 at some point. And it's n cubed. And we can do that only because we're doing a limit. Yeah, we're going to do it right now. So, did you like that? You think you can do that on the test?
Yeah, one problem. That's it.
Yeah, no
One problem test.
So now,
Are we gonna have access to the view? Is that I couldn't keep up?
huh?
Are we gonna have access?
I videotaped. Recorded it.
Where do we find it?
Did I put it? Yeah, I'll stick it in the modules. Yeah, I'll stick the YouTube link. What's it? I don't even know what he said. All right, I will go but get back because the next part is important. So take a minute. I'll give everybody a minute to let all that soak in because the next piece is the whole rest of the unit. It's important. So I'm going to wait a minute because people seem to need to go backwards, which is fine. So again, this is equivalent to the limit definition of the derivative. It's equivalent to doing that. It's just a lot more complicated. Okay? But does the idea make sense? If you take all these rectangles, because as you make them smaller and smaller, you get rid of those areas on the outside and those areas you're not using on the inside. And as you make them smaller and smaller, they become the exact area under the curve as you get to infinity. I hate these first 3 sections. I take a piece and go all around, so I'm just making sure I'm not skipping something that would have been mighty important as I skip around those first 2 sections. I'm going to stop this recording and call this one 5.1 and start another one for 5.2 because I think that makes more sense. Nah, I'll do it as one. Then they're kind of long. Yeah, it's all right. Hmm?
Can you have one popcorn? No. Can you only have one cookie? No.
So this leads into 5.2 where we are going to come up with, because remember, you did all those limit definitions of slope to find a derivative, and it was a lot of work. And then all of a sudden, I'm like, oh my God, I just had to multiply the exponent times the coefficient, and that was it, right? It was really easy. So now we're going to do the really easy. In 5.2, the definition of what we call, so what we did with the antiderivative is we kind of did this thing called indefinite integrals where we added c because we didn't know where it was and everything. The definition of the definite integral. So the definite integral is now an integral at a certain location between 2 points. So a function f defined on AB is integrable, that is a word, is integrable on AB if the limit as n goes to okay, this is what we just did. Now, I will tell you, there's another way of Lucy? That's where it starts. It starts at 1. You don't start at 5. Another variation I was using n going to infinity because it's infinite number of rectangles. If you think of it another way and think of your delta x for a second, what happens to delta x as n goes to infinity? Where does delta x go to? Think about it. Yeah, does that make sense? The more rectangles you have, delta x is getting smaller and smaller. So my point is, if you look through the notes, you might actually see this as delta x going to 0. It's the same idea. All right? It's the same idea. All right? So don't worry about that. Okay, if it exists, I don't need that part. And altruistic, this limit, then this limit is the integral from a to b of f of x dx. The symbol for integration comes from summing to infinity. So it literally is, if I take this and expand it enough, it looks like that. That's literally where the symbol came from. The symbol represents taking sums of the rectangles to infinity. So that's where the integration symbol kind of comes from. It's this evolution of a summation. So, definite integrals are really nice to work with. And again, I am jumping all over because I just don't like the way they work out this book. And it leads us to what we call the fundamental. That is really bad. And then we'll do the calculation. You'll see how easy it was. But let me get some definitions down first. The fundamental theorem of calculus. It took us how long to get to the fundamental theorem of calculus? The fundamental theorem of calculus is in two simple parts. All right. Part one just tells us that I guess I should put the rest of it on there. If f is continuous, on AB, then the area function. So the first part just relates that an integral is essentially the area under a curve. The area function a of x equals the integral from a to x. We're just going to call it f of t dt. They're just doing that because they don't want to get the x confused with an x across the line. Don't worry about that. For some x between a and b. So now this is another relationship. It's also going to relate, yes? Area function is defined as this. It also, this first part, this fundamental theorem of calculus, takes our area function and relates it back to the derivative. So it kind of also provides this neat little relationship. Then this area function, let's continue with, is continuous. And it's differentiable. Now, continuous, you can include endpoints. Do you remember with differentiable, you don't include endpoints when we did so it's A, B with parentheses. And the area function satisfies meaning if you take the derivative of the integral, what do you get back? The function. They undo each other, which we saw with the antiderivative. We've seen that relationship, okay? They're just, you can start at the starting point. They're just saying any x on that interval. It doesn't matter where you are on that interval. As long as you're continuous on that interval, yeah, it could be anywhere on the interval. So that's why they use x instead of saying x could be anywhere between a and b. I think, honestly, every textbook will do the definitions differently. I'm just using the definition in the textbook because if you're going to review, you're going to go back to the textbook, possibly. Maybe y'all never opened it. I have no idea. Yep. It eliminates the confusion, I guess. It's just saying it could be any function. The only thing that's really important with derivatives is this has to relate to that. They got to be the same. You can't have a function of x and put a dt on it. That's all. All right. Now, part 2 is what we're going to use to quickly solve the whole thing we did with the area between 1 and 4, that function 3x squared. So part 2 is the one that says, again, we got to state, if f is, again, everything goes out the window if f isn't continuous. Which is why we have calc 2 and calc 3. If f is continuous on AB, so remember using the notation that if you take the derivative of f of x, you use capital F, right, as the antiderivative. So this is the biggie. And that's what we're going to use right now. So basically, you take that antiderivative and then you plug in your upper limit minus your lower limit of your integral. So we're going to apply this right now. So this is your fundamental theorem of calculus. It basically, again, in the first part, it states that an integral is an area under a curve. That's what the fundamental theorem of calculus essentially states. It states the area, that an integral is an area under a curve. It also states the relationship between the antiderivative and the integral and the derivative, basically. It states that as well. And it also states how to calculate a definite integral. And we talk about a definite integral. What we're talking about is we are now doing it on an interval. That's what a definite integral has. It's actually on an interval, not going on where you add c because you don't know where it starts and you don't know where it ends. Now we know where it starts and ends. So let's go back to the one we did. This is going to be on the test a lot because your whole test is integration, essentially. What was that function again? I don't feel like scrolling back. Now I have really combined, let me identify that. I have combined everything from 5.1 to 5.3 in this lesson because I've eliminated the stuff I just don't think is useful. All right? And I thought it flowed better. All right, so let's do it. We want to do the integral. Oh, what was it again? It was also on, what was the interval? Okay. Why do I always want to do that? So when we do 1 to 4, this is our A, that's our B, correct? So when we're doing the integral, according to that definition, we're going to go from 1 to 4 of 3x squared minus x plus 9, and you just put this in here. You do that because you just don't know what x is. It's if you think back to the chain rule, you just don't know what x is, so you just put the dx on the end. That's something you'll get into more later. All right. Well, this just goes back to 4.9. 4.9, if you thought that was a section you could skip, you'd be wrong because you need it all through chapter 5. All right, let's do the integral first, and I'll show you some new little notation. So when I just forget the 1 to 4 for now, let's just integrate it. What's 3x squared integrated? Yeah, I'm going to put it all there, but yes, right? It's 3x cubed over 3, correct? That's how you do it. You raise it up, divide by what you just put in as the exponent. minus plus 1. Yes. That one I'm not going to put. Now, if we were doing an indefinite integral, how would we end this? Plus c. You don't need plus c, and I'll actually show you why algebraically in a minute. Instead of doing plus c, this is what you're going to do. New notation. You draw this line. And it's it. Let's put the actual values in. Wow, that really was bad. I'm getting used to it. Okay, that tells me I am going to evaluate this from 1 to 4. Name of what?
Of the line that we put at the end. Does it have
It's like half an absolute value. I don't know. I actually don't know the name of that. We just use it. I don't know. I'll look that one up though, because when I don't know something, that doesn't mean it doesn't exist, because there's a lot of things I don't know.
There's a lot of things that exist that just people watch wrong.
Yeah, but it's a way to just put it up there and say, okay, I'm going to evaluate it from 1 to 4. So what does that mean I got to do? Now I got to plug it in. All right, so I start with the 4. You're right, we can get rid of the 3's, right? We can cancel those. So I have 4 cubed minus 4 squared over 2 plus 9. Please use parentheses, because watch. What does this say we need to do? You got to subtract, right? Plugged in the 4 cubed minus 4 squared over 2, times 4, sorry. Minus, use parentheses, because honestly, this is where all the mistakes come from. Not using parentheses on that second set of parentheses. So now it's 1 cubed minus 1 over 2 plus 9 times 1. You just do the math. What's 4 cubed, everybody? Is it 64? Yeah. 8, is that 8? Because 4 squared divided by, yeah. 36 minus 1 plus 1/2 minus 9. All right, so forget the half for a second. Just do 64 minus 8 plus 36 minus 1 minus 9. I hope it's 82. Thank you. So it's 82 plus a half is... So what was quicker? Doing that? 82.5. We're doing all of that. You can do it this way on the test if you would like. You need a lot of scrap paper. That's it. Huh? So you don't use it for this, but you'll use the ideas around it for other things. Because you do a lot with series and summations. And there are times you do have to bring that in. You get into things like Taylor series and stuff like that. So you'll use components. It's a lot. But a lot of it comes from understanding the summation. So at least now you've seen it when you get it next semester. Because again, 2 full chapters on summations. Yes. I'm going to have you do, like you'll see, I'm not giving you the lab today. I'm giving you a break because we're not going to do that. We're going to do a couple practice with some of these. But one of the things is Tuesday will be a big lab day because we've covered a lot today. And I'm going to do a little bit more. I'll go to like 10:30 today and then I'll stop. Tuesday will be a big lab day. So the only thing as I scroll up that I will make you do on the test is one of these, where I give you n, but I won't make you go to infinity.
Yeah, what I'm saying is that by using the rectangles inside the area, we're not going to find a set value. It's going to be right?
It's going to be an approximation unless you take it to infinity.
Yeah, are we going to
No, you're going to use this instead of taking that to infinity. This is what you're going to use, because look at the difference. That was easy. So let me give you one of these to do. Let me have you try one of these. I won't jump to trig functions.
Thank you.
Let's do radical. Get your calculators out. And let's do from 4 to 16. Before we do that, I want to make one comment before we do that. I want you to see for a second why we don't need to put those C's in, okay? And I want you to think about it this way. We don't know what that constant is. Even here, we wouldn't know what the constant is. If I plugged it in here, it would be plus C, right? And over here, I'd have plus C. But that plus C over here becomes what? Minus C. So I have a plus C minus a C. What happens to it all the time? It goes away. That's why you don't need to worry about it. When you're doing a definite. What you need to be careful of, how do you know if it's a definite integral versus an indefinite? Well, that's easy. Indefinite, definite. Definite has the upper and lower bound on it. Mm-hmm. Yep, definite integral is your area. Yep. All right, go for it. Well, it depends on what f is. You're not doing 7 minus 5. Yeah. It works. We just saw it. It works. I know. Sometimes, Damien, for now, you're just going to accept things and say, and you know what? If you're that interested, you're going to take a lot more math courses, and you're going to figure it all out. Oh, sorry. Whew. All right, just go ahead and do this one for me right now. Why would you say that? Let's say right here. There are companies that do hire math majors, but a lot of people will major in math and then use it to go on to other things. There's a lot of master's degree programs that you can do with a major in math. One of them was it was popular back when I left college, was like quality control. They would take a math major and you get a master's degree in quality control and work for a company and you do make a lot of money. I don't know how many jobs are out there today, but I would say a lot. Unfortunately, they also a lot of times they want the application. So they want the engineering or the computer science or whatever else. Yeah. It's good to get a foundation now at the community college. Yeah. Take all the math courses because then you got them done. So let's do this. Get an answer. And then we're going to talk a little bit about net versus total areas. And then we'll be pretty good from 5.1 to 5.3. Oh, I don't know yet. Hold on a second. You got something you don't think is right?
So they use just take it to the reference or whatever functions react, and then when you get the plus C, you can't see it, you can't also put the stick, or you plug in 16 to the equation, and then you subtract the whole equation. So 3 to square root of x is 2x to the 3. Square root is to the half.
Yeah, I think the hardest part of this is the square root of x, right? X to the 1/2.
I'm pretty sure I did this awfully wrong. That's what I have.
So you got 3 to the x plus 1 divided by 1/2. That might be right. Oh, I did have an answer. Because I picked one out of the book that had an answer. Let's just check it. Which one was it? Which one did I just do? B? Got 112. 112. Because what's 1/2? So you got your 1/2 divided by. So you got your 2. So probably when you did your evaluation of 16, keep it as a fraction. It makes it easier. So this is x to the 3/2 because it makes it easier to do the.
Okay.
So you were good up to that point though. Just something when you did your calculations. All right, you ready? What kind of answers we getting? All right, so the first step, obviously, there's a couple things you can do. You can pull the 3 out and not worry about it. It doesn't matter. But 3, this ends up being, so x to the 1/2, you're adding 1, right? So it's 3/2 divided by 3/2. So you got to figure out 3 divided by 3/2, which is 3 times 2/3, which is just what? 2. Right? So it ends up being 2x. I would keep that as x to the 3/2 because it'll be easier to do the math. From 4 to 16, right? So it's 2 minus 2, 4 to the 3/2. Yeah, so when you're looking at something like 16 to the 3/2, remember you do the square root first. So the square root of 16 is 4. 4 cubed, right? Square root of 4 is 2 cubed. So 128 minus 16 is 1. Yeah, yes. Do the square root. Yeah. If not, use your calculator and do that button A to the A over B button. You can do it the other way. It doesn't matter because you can. But then I can't cube 16 in my head, but I can take the square root. You understand what I mean? Yeah, yeah. I'm just like if I was doing it in my head, it's a lot easier for me to take the square cube 4 than to cube 16 in my head. Yeah. Yeah. So the last you just did that. It sounded good. 4,096 sounded good. The last little piece I'm going to go over so that you can over the weekend, my suggestion, there's a lot of little intricacies I probably need to go back to and doing it the way I did this today, 5-1 to 5-3. So if you get problems in Math Lab, hopefully you do that over the weekend. You can work on Math Lab from 5-1 to 5-3. You can shoot them off to me so it reminds me of something. Oh, I might have missed talking about that or something along those lines. But the last little piece, and I said I was letting you go at 10:30, is the net versus area. So we've only looked at areas that are above the curve so far. All right, but if you're doing just so I'll just draw a funky picture. So let's do the green is clearly below, right? And the red is above. And suppose I have, this is my A. We'll call this B, and that's C. All right, first of all, there's a difference between net area versus area. Okay? When we talk about the area, if we were to do the integral from A to B, you will get a negative value. All right? It'll definitely be negative. So the integral here, let's just come up with a number. All right, I'm going to call it -4. I don't know what it is. Let's call it -4 for the area. And let's call the area in red, which is a positive area of 5. Okay? So just real quick, forget integration and everything else. Net area is exactly that. The net area from A to C would literally be -4 plus 5 equals 1. Okay? Now there's net area, and then there's the other area the book just calls area. Think of it as total area. Total area is we get rid of the idea that it's negative. We want the total area, meaning I want to know the area of everything shaded. When you're looking at it this way, you have to think of that -4 and take the absolute value of it. All right. So net allows you to work with those negative areas and keep them as negative areas. Total area, we think of it as an absolute value, and there's different ways to do it. You can take the absolute value of the integral from A to B, right, plus the integral from B to C. Or another way that the book or anyone will write it out, say, okay, I know this area is clearly under the curve, so I would do negative the opposite of the area from A to B. Don't they essentially mean the same thing? So the point of me showing this to you is if they're talking about a net area, you are to use the negative. Because if you do take an area of something under a curve, it will give you a negative value. So I'm trying to prove it to you. What would be something that we know? Let's do x squared minus 5. All right, where's the x squared minus 5 graph, everybody? And it, oh. Yeah, no, that's fine. Right? Okay, that's fine. So let's do that from 1 to 3. In other words, I want just that area. Does everybody see that? So I want the integral from 1 to 3. Go ahead and calculate that area. Let's calculate. We'll do it together real quick. All right, what's the derivative of x squared minus 5? And I'm integrating from 1. I'm evaluating from 1 to 3. So let's plug in 3. What's 3 cubed? Okay. What's 3 cubed? 27. I had 27 in my head, and he said 81, and I swear I almost wrote down 81. 27 over 3. Yeah, I know. I'll get there. Minus, plug in 1. All right, what's 27 over 3? Minus 15. Minus a third. Plus 5. That's negative 10, negative 1 minus 3. Yeah, negative 1.333, correct? I just want to prove to you it's negative. That's going to happen anytime your area. So when we're talking about, you just got to be careful, because if you want total area, it's a little bit different. If you want total area between 1 and 3, now we're talking positive. Where this gets tricky and what you'll see in math lab, what is that? So the area, the sine curve, right? From 0 to 2 pi. The net area without doing any work should equal what? So if this truly is a sine curve from 0 to 2 pi, what should the net area equal without doing any work? Because we know in the sine curve, the area above is going to be equal, so it's going to equal 0. So you got to be real careful. Usually, they will say net area. If net area is not stated, then there's different ways you have to kind of split it up, right? If net area is not stated, you would literally, to get total area, there's different ways to do it. You can see it's symmetric. There's different ways to look at it. But you would technically need to do the area from 0 to pi and add it to the absolute value of the area. So I think it's like 1. I think the area under the sine curve, the piece of it, I think, and that comes to 2. But I'm saying that off the top of my head, so don't. I think you get a problem like this, so I just want to leave it like that. Just kind of show you. So there's a lot of little tiny things we didn't talk about, but you've got the gist of 5.1 to 5.3, which is good. If you, between now and Tuesday, can go through math labs and send me some that seem a little, I don't know what I'm doing, we can kind of go back and fill in some of the holes. So, a lot of integration, and we got to reverse the chain rule. USUP, it's called USUP. That's the big piece. Yeah, it's we've pretty much done most of the chapter, except for USUP. And then we're going to look at area between houses. But this is the bulk of it. It really is. Don't let today fool you. It really isn't easier.